So we've seen a number of different examples of coordinate systems in 2D. We also want to see a number of different examples of coordinate systems in 3D because these are also going to be very, very useful as we kind of go along further into our study of multivariable calculus. The idea is that in this class we'll focus on what are called cylindrical coordinates and spherical coordinates. What I'm going to do right now is just kind of discuss the general coordinate system in 3D, as well as these specific examples of spherical coordinates, polar coordinates, and then I'll give you a couple more different applications in examples. So, coordinate system in 3D is a mapping where x is a function of new coordinates u, v, and w. Y is a function of new coordinates u, v, and w. And z is a function of new coordinates u, v, and w. And just like in 2D for two variable coordinate systems, the most useful tool at our disposal when trying to understand these coordinate systems is going to be the Jacobian matrix. Which, just like in 2D, is of very real sense the first derivative, if you will, of the coordinate transformation, of the mapping of three-dimensional space. So this matrix, just like in 2D, for 2D coordinate transformation, is the matrix of first partial derivatives of the Cartesian coordinates, x, y, and z, with respect to the new coordinates u, v, and w. And much like in the 2D case, we treat the columns as the derivatives of each individual Cartesian component with respect to each individual variable u, v, or w. So the first row here is going to be all of the derivatives of the x coordinate with respect to first u, then v, then w. And the second row is going to be the derivative of y with respect to u, v, and w. And the third row is going to be the partial derivatives of z with respect to u, v, and w. Which means that just like before, we can think of the rows as the gradient of the Cartesian coordinates with respect to the new variables u, v, and w, or we can think of the columns, and this is the more useful geometric interpretation, and one of the things that we're going to use a little bit later on. The columns here are, first column is the derivative of the position vector in Cartesian coordinates, r, with respect to u. The second row is the second column is the partial derivative of the position vector in Cartesian coordinates with respect to v. And the third column is the partial derivative of the position vector r in Cartesian coordinates with respect to w. So this matrix is going to be extremely useful a little bit later on. So let's jump into some specific examples of different coordinate transformations in 3D. So the first example that we'll consider is what's called cylindrical coordinates. This is really, in some sense, very, very similar, if not the same, in some sense, as polar coordinates, where you pick an axis. Typically, we pick the z-axis, but you can do this along x-axis or y-axis as well. We say that x is equal to u times cosine of v. Y is equal to u times sine of v. And z is just equal to w. And this is for u from 0 to some radius r, maximum radius. V is from 0 to 2 pi, and W just goes from a minimum z value to a maximum z value. And what this coordinate system is essentially based on is cylinders. And if we view the coordinate curves for this coordinate transformation, we get a very good idea of how this is describing all points in 3D. So that's what we're going to do right now. And here we see a plot of the coordinate curves. I specifically started with the XY axis, so you see that this is very similar, if not the exact same, as our normal polar coordinates, where points in 2D are described by level curves of this transformation that are circles and correspond to fixed values of the radius. In our coordinate transformation, it's u, and the orange here are fixed values corresponding to the angle v, which is the angle around the x-axis. You can do this around any one of the axes, but you have to pick an axis if you're going to do cylindrical coordinates. We've picked the z-axis to be our axis of symmetry. And if we rotate this coordinate curves here, this is actually a picture that I made in 3D. We see points are essentially being picked on cylinders in 3D. And you can very clearly see that the z-axis here, these magenta lines are corresponding to fixed values, or continuous values of w, and if you fix a value of w, you get one of these cross sections, where then the values of u and v determine the point in three-dimensional space. So this is a very neat diagram, I think, showing exactly what cylindrical coordinates is doing and how it's sort of re-expressing three-dimensional space. Now, cylindrical coordinates, much like polar coordinates, are very useful in a number of different circumstances, but mainly if you have some sort of symmetry around one of the axes of the problem, some sort of symmetry around the z-axis or the x-axis or the y-axis. And this is the key to sort of knowing, when to use a particular coordinate system. Sometimes it will simplify the domain that you're considering. Other times it'll simplify the function that you're considering. But the key thing in determining, what the proper coordinate system to use is what the various symmetries of the problem are. Whether that's in the domain that you're trying to consider, or those symmetries are in the actual function that you're looking at. Now, we said before that for coordinate system in 3D, we can write down the Jacobian of the Jacobian matrix of the coordinate transformation, and I want to do that right here for use in future problems. So the Jacobian matrix of this coordinate transformation is going to be the x partial derivative, or the u partial derivative of x, which will be cosine of v, the v partial derivative of x, which will be negative u sine of v, and then the w partial derivative of x, which will be 0. then we have to do with the y partial derivatives. The u partial derivative of y will be sine of v. The v partial derivative of y will be u times cosine of v. And the w partial derivative of y will be 0. And for z, the u partial derivative of z will be 0. The v partial derivative of z will be 0. And the w partial derivative of z will be 1. And this is the Jacobian matrix of this coordinate transformation. This also means that this column right here is the u partial derivative of the Cartesian position vector. This column right here is the v partial derivative of the Cartesian coordinate position vector. And this last column right here is the w partial derivative of the Cartesian coordinate position vector. The next coordinate transformation that is really important in applications that we'll use a lot is called spherical coordinates. And this coordinate system requires a little bit of an explanation. So this is what I'll go through and do right now. I'll kind of give a little bit of a derivation of where these coordinates are coming from. And so what I've drawn here is just an x-axis, a y-axis, and a z-axis in 3D, as well as a point, which is the point, say, r, in Cartesian coordinates, x, y, and z. And spherical coordinates is, in some sense, related to polar coordinates, so it's sometimes called spherical polar coordinates, just like cylindrical coordinates are sometimes called cylindrical polar coordinates. And what we can do here is relatively easily describe the location of this point using some basic trigonometry. So we know that if we take this point in 3D and we look down at its intersection in the xy plane, it's going to intersect with the xy plane at some point. The radius out to that point is r, and that distance is also the same thing as this distance right here from the z-axis. The same, say, r, you can think of it like the r from cylindrical coordinates. But what this does is create a big triangle for us in 3 dimensions. And this triangle has this angle right here, which is our w coordinate, also sometimes called phi in many sources. This is the angle subtended down from the z-axis to the wherever this point is in 3D. And we have immediately that the z coordinate of this point from trigonometry, z, is this distance right here. This is going to be equal to the distance out to this point, which we'll call u. This is the radius of this point, or the radius out to this point in 3 dimensions. Z is going to be equal to u times sine of w. So in this picture, the length of r is equal to u. The norm of r is equal to u. So the norm of r, the vector r, which is the square root of x squared plus y squared plus z squared, is the same thing as u. From basic trigonometry, sine of w is this distance right here divided by u. So it's z is going to be equal to u times sine of w. This also means for us that r, which is the distance in the xy plane out to this point right here, this is going to be equal to u times cosine of this angle w. And then what's kind of neat here is that using cylindrical coordinates, we know that the x coordinate and then as well the y coordinate can both be got using what we know about cylindrical polar coordinates. That's x is equal to r cosine of v, and y is equal to r sine of v, which ultimately then gives us, when we plug in, that x is equal to u times cosine of v times cosine of w. Y is equal to u sine of v times cosine of w. This is what we get when we plug in this r right into the formula for y from cylindrical coordinates. And z, then we know from before, is just u times sine of w. And this is the correct relationship in general for spherical polar coordinates. Now, the book uses slightly different notation, right? In the book's notation, in many books on multivariable calculus, you have that u is equal to rho, v is equal to theta, and w is equal to phi. But really, this is just a notational difference, right? The main kind of structure and idea here of spherical polar coordinates is very clearly shown here. And in general, we're using u, v, and w for our new coordinates, so I want to stick with that. But this is an extremely important coordinate system if you have, say, spherical symmetry. So any problems where you have either your domain that you're considering or the function that you're considering is spherically symmetric, this coordinate system is going to be extremely useful. And so the Jacobian matrix, which gives us, in some sense, the all first order rate of change information about this coordinate transformation, is going to be the u partial derivative of x, which is cosine of b cosine of w, the v partial derivative of x, which will be negative u sine of v cosine of w, and the w partial derivative of x, which will be negative cosine of v, or negative u cosine of v, sine of w. I'll make a little bit more space here. And then the y partial derivatives will be the y partial derivative with respect to u, which will be sine of v cosine of w, the y partial derivative with respect to v, which will be u times cosine of v cosine of w, and then the y partial derivative with respect to w, which will be negative u sine of v sine of w. And then lastly, the z partial derivative. The z partial derivative with respect to u will be sine of w. The z partial derivative with respect to v will be 0. And the z partial derivative with respect to w will be u times cosine of w. So the Jacobian matrix for this coordinate transformation is a little bit more complicated than for cylindrical polar coordinates. However, it does simplify nicely in certain aspects when we actually go to use it in doing what are called triple integrals for in spherical polar coordinates. So we won't be getting into this in this lecture, but we will be using this Jacobian matrix a little bit later on, which is going to be a very important idea. Now, visualizing these coordinate curves can sometimes be a little bit tricky and hard to see. I think the explanation that I gave before was a decent explanation, but what I did was I also plotted out these coordinate curves in 3D so you can kind of really get a taste for exactly what we're doing. So just like for cylindrical coordinates, I've started out by just plotting the x, y plane here in various coordinate curves at different levels of z, so you can get an idea of what this is looking like in the xy plane. And just like in the derivation, you're seeing that all of these points in 3D that I've plotted out in the xy plane are intersecting on circles of varying radii at varying angles as well. So here we have the green curves are fixed values of the radius going outwards, and the magenta curves are just fixed values of the angle theta from the x-axis. But if we rotate this to really get a feel for what this is looking like in 3D, right, we're seeing that these coordinate curves in 3D are directly describing fixed values of the radius u. These are these magenta curves being measured away from the origin here, in fixed values of the angle w coming down from the z-axis, and then lastly fixed values of the angle v, which is the angle measured from the x-axis with respect to the z-axis. And you're seeing very clearly that these coordinate curves are related to spheres of varying radius. And this is how we are describing points in 3D in this coordinate system. This is a very neat picture, I think, and a very neat idea. And it is super useful in applications in which we have some sort of spherical symmetry, either in the domain, right, that we're going to be using or investigating, or in the function itself that we're going to be investigating. And I just want to emphasize here what values, right, where u is, where v is, and where w is here. This is very important to do. In general, u ranges from 0, which is the origin, all the way up to some maximum radius away from the origin. V, the angle from the x-axis, is in general an angle from 0 to 2 pi, or all the way around the x-axis here. In w, v is from 0 to 2 pi, w goes from 0 to pi, or 0 being the z-axis here, the upper positive z-axis, down to pi, which is the negative z-axis. and we can clearly see this on this picture right here, that we need these ranges for W to go from an angle of 0 to an angle of pi, and then theta to go from an angle of 0 to 2 pi, and then the radius outward goes from 0, which is the origin, all the way out to the maximum radius that we want to consider. And this will describe any and all points that we want to describe in three-dimensional space. And what I want to do is present an example of where coordinate systems sometimes, I shouldn't say sometimes, very often come in and simplify certain problems and allow us to analyze certain problems with physical symmetries. And this is an example that's very, very closely relevant to students in this course. Years ago, maybe in the early 2000s, there was WPI MQP that actually partnered with Bose and utilized what are called helical coordinates, so coordinates that are based on the helix, to analyze forces, Newton's laws, on screws in certain audio components that were being manufactured by Bose. This is the third example, and it's kind of an application example of helical coordinates. And we won't really be going through this coordinate transformation in this class. We'll mainly be using polar and cylindrical coordinates in this class in 3D, but I do want to show you a picture and show you this example that this WPI MQP group and this actually spawned a number of different MQPs. To analyze the forces on a screw in a Bose device. And what I'll do is show you a picture of helical coordinates, and I'll also show you a picture from this report that actually is a very convincing picture. So this is a picture of the coordinate curves in the XZ or the XY plane for varying values of z for helical coordinates, and it doesn't look too illustrative now, but if we sort of rotate this a little bit so we can see the z-axis here and really see what this is telling us in 3D. And this coordinate system is clearly based on helices and is symmetric, right, with respect to helical curves going along the z-axis. And what this MQP group was able to do was use this coordinate system to go through and analyze Newton's laws, Newton's force laws in this coordinate system, and get very convincing curves for the force on the screw that really matched up very well with experimental data given by Bose. And here I've just included a diagram of the from the actual paper that I'm referencing, which I'll post on the course website. And you can clearly see that a helical coordinate system is the most appropriate coordinate system to use when modeling a screw. And not only that, but this model that they were able to get from this model produces results agreed with experiment very, very well. Here, the blue curve is the experimental data. The red curve right here is the mathematical model that was produced by the analysis of Newton's laws using helical coordinates. And you can clearly see from this image that the model for the torque as a function of the angular rotation of the screw is very clearly predicting what's happening in reality in experiments. So I think this is a very neat application to show of a relatively straightforward application of coordinate systems in 3D. It's also very fitting because this class is a class at WPI, and this is coming directly from a WPI MQP. So the last example, application that I want to talk about in today's lecture is going to be what are called partial differential equations, and really these are not an application of coordinate systems, right? These are an applications in general of multivariable function. Now, coordinate systems do very often come up in the most convenient way or the simplest way of modeling a particular partial differential equation problem. So this is why I've included this application in this lecture. But more generally, a partial differential equation is an equation that is essentially relating an unknown multivariable function and its partial derivatives. So a PDE, or partial differential equation, is a mathematical equation, and it could also be a system of equations that relate an unknown multivariable function and its partial derivatives. And this would be a function or functions and its partial derivatives in the case of a system of partial differential equations. These are super important in describing really any modern physical law, and they have applications really all over, not just in physics, but in economics, in biology, in many different areas. And I'm not going to go over the derivation of any of these because that's a topic for an entirely another course, but it's good to be familiar with them at least, so I will write some of them down a little bit later. But typically these are derived from physical or other, in the case of, say, an economic application, assumptions on the functions considered. And the two example PDEs that I'll talk about today are from two different applied scenarios, one being heat transfer, the other being from mechanical engineering, so mechanics, or electrical engineering, or electrodynamics. These are the heat equation and the wave equation. So these are the two examples that I'll talk about as we move on. So the heat equation is a partial differential equation that describes heat flow through a given material. in general, it's a function of a number of spatial variables, so possibly 1, 2, or 3 spatial variables, and always it will also be a function of time as well, because the temperature at every given point is changing in time. So the dependent variable in these problems is the temperature. This is the unknown function that we're trying to solve for, and we typically denote it by U or T. So this is a display of the heat equation. We call it the 1D heat equation, the 2D heat equation, and the 3D heat equation. Now don't let the 1D, 2D, and 3D fool you. The 1D heat equation's solution is actually a function of 2 variables, because it's a function of one-dimensional position, so spatial position, and time. And it's exactly given by this relationship right here, saying the first partial derivative of temperature with respect to time is equal to some constant k times the second partial derivative of temperature with respect to space. Similarly, the heat equation in 2D is going to be the partial derivative of temperature with respect to time is equal to constant k times the sum of second partial derivatives of the temperature u with respect to the spatial coordinates. So in general here, in each one of these cases, u is the temperature, at a point in space and time. And this is a dependent variable because it depends on the spatial variables and the time variable. The independent variables in a heat equation problem would be the spatial coordinates r. In the most general problem, it's x, y, z. But in the 2D heat equation, you just have x and y, and in the 1D heat equation, along, say, a bar, you just have x. But in general, the independent variables would be the position coordinates in the medium that you're discussing the heat flow, and time, because the temperature depends on these independent variables. And lastly, k here is sometimes called the diffusivity of the medium. Right, and this coefficient basically is describing how well or how not well heat diffuses through the medium under consideration. So this depends on various material properties and the geometry under consideration. But these equations are probably the simplest equations, partial differential equations, that describe heat flow through a given medium. If you take a heat transfer course, you'll really delve into this in depth. But the idea here is that we just want to kind of get an idea of what the solutions to these equations look like. And the solutions are exactly what you would expect for any number of dimensions that you want to consider the heat equation. That for an initial temperature distribution, the solution to the heat equation gradually smooths out that temperature distribution. So here we see a plot of an initial temperature distribution, say along a 1D bar as a function of x from 0 to 1, where in the middle of the bar is the highest initial temperature, and at the ends of the bar the temperature is fixed at 0. As time evolves, we expect for the temperature to sort of flow and decrease so that the temperature stabilizes. And this is exactly what we see when we solve this heat equation. So what we just saw was an example of the heat equation being applied in 1D to a 1D bar. This next picture is a picture in 2D, say maybe a two-dimensional plate of width 4 along the x-axis and of width 5 along the y-axis, with an initial temperature distribution in the middle of the plate. So we'll say that the temperature is 0 except for some like small rectangle in the middle of the plate. As we go about solving the heat equation, the temperature distribution will gradually smooth out, and this is exactly what we see. Now, actually solving equations like this is actually quite difficult, and we won't be getting into solving for general solutions to PDEs. This is an entire course or multiple courses worth of work to really understand the mathematics behind this, and it requires a lot of advanced ideas. So if you're interested, I recommend taking an engineering mathematics class or a boundary value problems class after taking the required prerequisites. But it's good to be exposed to these ideas at an early stage, so you can see how these are used in real-world applications. The next example partial differential equation that I want to reference and mention is called the wave equation. And simply put, this is an equation that describes the propagation of waves as they travel through some medium. These waves can be mechanical waves, so you can think of like, say, an elastic bar. If you hit one end of the elastic bar, how the resulting disturbance is going to travel through the bar. These waves could also be electromagnetic waves propagating through some medium, and really, even in certain cases, you can use the wave equation to study water waves, which actually are governed by very, very complicated, what are called nonlinear partial differential equations for the full description of the water waves. But the basic wave equation, the standard wave equation, is what's called a linear wave equation, or a linear partial differential equation, just like the heat equation as well that we just talked about. So I've just written down here the standard wave equation in 1D, 2D, and 3D, just like I did for the heat equation, where we see that the wave equation along a 1D elastic bar, say, or a 1D medium, is saying that the second derivative of u, where u is the disturbance, the wave disturbance at some point along the bar, it's a function of x and t in the 1D case. The second derivative of u with respect to time is equal to a squared times the second derivative of u with respect to space. And in 2D and 3D, we have similar wave equations. So the dependent variable here is u, because it depends on the spatial variables and the time variable. This is the magnitude of the wave disturbance. At a point in space and in time. And really, if you think of, say, a one-dimensional elastic string, like maybe a piano wire or a string on a violin or a guitar, you can think of a really good interpretation of what this 1D wave equation is giving us the solution to. If you say pluck the string, the value of u is the displacement of the string at any point along the string and any point in time. The independent variable, or variables, are the position, which in general, 3D case, is a three-dimensional point, and then as well as time as well, because the magnitude of the disturbance at every point in space and in time depend or depends on the point in space and the time t. The last value to consider here is this value a, which is a coefficient value that is actually giving you, at any given point in space, the wave velocity, wave speed. So this is the propagation speed of the wave. And so the guitar string example that I gave before is a very good example of the wave equation in 1D. What I'm going to show you now is an example of the wave equation in 2D. So 2D wave equation at any point t, any value t, gives you a function of two variables, which is of x and y, for any fixed value of t. And we can visualize that as either a surface plot or a density plot, as we've seen in many different examples that we've covered. So if we consider, say, a two-dimensional elastic membrane, where at a certain point in the membrane we stretch the membrane up and then let it go, and consider the resulting wave propagation, or the propagation and the disturbance of the membrane, this is what we're seeing right here. So this is an animation showing the solution at various times t. And we very clearly see the motion of this disturbance, and not only that, the interaction of this disturbance with the various boundaries in the problem. Three of the boundaries are fixed boundaries. One of the boundaries is set to be a free boundary. But the idea here is that this is very clearly showing us the resulting solution to the 2D wave equation that we were talking about before. Now, like I said before, solving for the general solution to a PDE is in general a very difficult task. And we will not be going over that in this course because it takes a lot of effort and understanding, a lot more than we have at our disposal right now. However, it is within our power to verify that a given function satisfies one of these equations, the heat equation or the wave equation. So, for example, I'll just end with the example. Let's show that the function u of x t is equal to sine of x minus ct plus cosine of x plus ct satisfies the 1D wave equation. So we can go through and do this. We're definitely within our power to go through and do. All it matters, or all we need to do, is take the second partial derivative with respect to t. Well, the partial derivative of this function with respect to t is going to be cosine of x minus ct times negative c plus negative sine of x plus ct times c, or c times cosine of x minus ct times -1 minus sine of x plus ct. And so the second partial derivative of u with respect to time is going to be the partial derivative of this function with respect to time, which will be c times, and this negative sign, you derivative of cosine is negative sines. The negative signs cancel out. Then when you multiply through the chain rule, you get sine of x minus ct times another negative c from the t partial derivative of x minus ct. So the second partial derivative of u with respect to t is going to be c squared times negative sine of x minus ct minus cosine of x plus ct. And next, we got to go through and do the spatial derivatives. So du dx and du dx, take the x partial derivative of this original function right here. We're going to get cosine of x minus ct times 1, and then minus sine of x plus ct times 1, chain rule. So the second partial derivative of u with respect to x is going to be negative sine of x minus ct minus cosine of x plus ct. And you see here that because this now we've shown is d squared u dx squared, this function right here, this is the same thing as d squared u dt squared over c squared, or right, this is just c squared times d squared u dx squared, which is exactly the 1D wave equation. So this function satisfies the wave equation. Right? This is one possible solution to the wave equation. Now, the trick and the difficult part about all this is going through and actually doing the opposite thing, which is giving an initial condition or a boundary condition, and going through and solving for the exact solution for a specified initial and boundary condition. This is the stuff that's very difficult about solving PDEs, but going through and verifying that a given function is a solution is a little bit easier and possible to do just with the partial derivative material that we've covered in this course. And so I went into Desmos to create an animation to show you very clearly that what we just computed is correct. So this is just a plot of the function cosine of x minus ct plus sine of x plus ct, and we verified this in fact does satisfy the wave equation, which means if we plot this out for, say, c equals 2.6, that's the wave propagation speed, as well as, say, various values of t, we expect to get oscillatory wave-like behavior. This is exactly what we're seeing. Let me zoom out a little bit so we see the entirety of this. If I change the value of c, this results in faster propagating waves. If I lower the value of c, this results in slower. And if I even change the function a little bit, so I just removed a portion of the function here. It's a new function, but verifying that it satisfies the wave equation is a little bit very similar to before. This is just a propagating wave traveling to the right, x cosine of x minus ct. And so I've changed that input function one more time with another solution to the 2D or the 1D wave equation. You see very clearly that we're getting results that are oscillatory, and if you were to go through and calculate the partial derivatives at any one of these points, you would very clearly see that it's satisfying the 1D wave equation. But this will conclude our lecture for today. Thank you very much for tuning in. I hope you learned something and you had a fantastic day.